Okay, hello everyone, and thank you for joining today's TVS Science Colloquium. We are finally back after the summer break, and it's great to see so many of you here today. So as usual, I would like to first inform you that this talk is being recorded and will be later uploaded to the TVS YouTube channel. And after the presentation by our speaker, there will be plenty of time for your questions, so please save them until the end of the talk or just type them in the chat. And now I would like to give a very warm welcome to our speaker today, James Hitchcock. James is a PhD candidate in astrophysics at the School of Physics and Astronomy at the University of St. Andrews. Sorry. His research has been centered around taking advantage of the structural similarities between astronomical image modeling and deep learning problems. To that end, he has developed the image subtraction code, PyTorch DIA, and he is currently working on a multi-frame blind deconvolution tool for high frame rate image applications. Today, James will tell us all about difference image analysis with PyTorch DIA. So please, James, the floor is yours.
Thank you very much. A nice introduction. Hi, I'm James. I'm a PhD student at St. Andrews. And as was said, my research is focused around this one idea of trying to leverage structural similarities in a subset of machine learning problems and astronomical image processing and modeling. So to introduce that, I'll just start with a definition. So this is my practical working definition of what an image is. So images are just convolutions, specifically two-dimensional convolutions. So telescopes are just analog convolution machines. And very many of the useful image models which we work with in astronomy can be described as such. And in machine learning world, there's a subset of problems that share this structure. So most notably, perhaps convolutional neural networks. So these are massive models, but they are composed of very many of these 2D convolution operations. And that operation looks something like this. So we have two images, a small one, which we call the kernel, and a larger one, which we can just classify as being the input. And the convolution of these two things is just the scalar product between the elements in the kernel and the elements in this input, and the kernel slides over the input in some sliding window fashion. And then we may have some additive bias term, which can be a scalar or another matrix, as long as it's the right shape. And then this gives us some output. So this is the core operation in a load of machine learning architectures. And it also happens to be exactly analogous to very many image models that we encounter in astronomy. So just to give you one example, here's the model for an image as observed by a telescope. And so if we point our camera at some astronomical scene, that thing then gets convolved with the points per function of the observing system. And then we have something added onto the end, like some smooth background. So there is this quite striking similarity in structure. And so the idea behind what I've been working on is, well, given that this operation is incredibly well supported in various machine learning frameworks, can we use those frameworks to work with models that look something like this? So when I first started looking into this with collaborators back in late 2019, early 2020, there were two big names in the landscape of machine learning frameworks. First of which was TensorFlow, which was released in 2015. And the following year, PyTorch came out. And by the title of the talk, you'll probably guess that I ultimately went with PyTorch. The simple reason being that I just prefer the syntax and the documentation. Like most astronomers, I pretty much exclusively work in Python these days. So the relative learning curve to getting to grips with this stuff was pretty shallow. But everything I'm describing today that I've applied in PyTorch, as far as I'm aware, can be achieved in TensorFlow. And similarly could be achieved in JAX. So this is the new kid on the block. This was released by Google in 2020. And if you're unfamiliar with either PyTorch or TensorFlow, this, I would suggest, be the first port of call if anything I say today sounds interesting and worthwhile trying in your own research, simply because if you have any NumPy code, this thing can be used as a drop-in replacement for that. But just going back to PyTorch, so you'll see that this thing is described as this open source machine learning framework. That's a good definition of how it's normally used. But for the purposes of my own research, it's a much more useful definition is to drop the machine learning element altogether and just think of this as some generic modeling tool. So just to be absolutely clear, because I understand the title of this talk can be somewhat misleading, I don't do machine learning, but I am trying to repurpose the tools for some specific image modeling problems that we encounter in astronomy. So I guess the next step is to just specify what that problem is. So I fit image models to data, and this will typically involve some nonlinear but inherently massively parallel optimization problem. So these optimizations are nonlinear because we have to contend with photon noise. So this is Poissonian. So the variance is dependent on the models. It's dependent on the expected number of counts, actually photon counting statistics. But operations on images are embarrassingly parallel in the jargon, because operations that we perform on pixels are independent of all other pixels in the image. So if you have the right hardware, you can potentially exploit that. So how on earth is PyTorch useful for addressing that sort of problem? So getting into specifics now. So first off, these frameworks come with highly optimized convolution computations that you can easily run on the GPU. And I stress the word easily there. So PyTorch, it is a Pythonic tool, but the functions that you're calling are going to be either written in C++ or in CUDA. So it's performant while still being nice and readable, and development is usually pretty quick. So CUDA is NVIDIA's GPU-specific programming language, and PyTorch comes bundled with this and other nice accessories like cuDNN right out of the box. So in the context of convolutions in particular, this cuDNN tool is particularly useful because this automatically, that is behind the scenes, takes care of the previously somewhat challenging task of memory management, like moving in some optimal way a memory onto your device accelerators. And also it comes bundled with efficient algorithms for performing convolutions themselves. And again, that's all taken care of automatically for you. So you can just focus on the science and the program aspect, like the technical details of the GPU programming is done automatically. So that's very useful. The second feature is automatic differentiation. So image models, now I'm typically fitting models with at least the order of 100 parameters, if not thousands or tens of thousands. So if you're fitting large models like this, it's incredibly useful to have exact gradient information. Right? Numerical, noisy approaches to optimization just will typically fail in that larger parameter space. So that's very useful for that reason. And a secondary benefit of this tool is that you have a certain flexibility here with reparameterizing models and trying out different models and different problems. Because of the fact gradients are computed automatically, you don't need to manually recompute these, right, every time you change the parameterization. So that makes experimentation quite straightforward. It's certainly a quality of life feature. So just briefly, if you're unfamiliar with how this works, just to give a very high level overview, automatic differentiation is basically the chain rule applied to code. So say we write some function in code, some f of x, which might be your objective function in an optimization scheme. Although we don't know the derivatives of this thing with respect to our model parameters that we're attempting to fit immediately, we can recognize that we can decompose pretty much any function into a sequence of simple elementary operations. So, additions, multiplications, exponential functions, trigonometric functions, and we can compute the derivatives of those. So those are simple derivatives to compute. So if we make a graph of all that sequence of operations, we can just then work backwards through it, just applying derivatives as we go. just by applying the chain rule, and then ultimately end up with what we the derivatives with respect to our input parameters. The third tool, and this again is more of a quality of life feature, the optimization algorithms are built into PyTorch, and there's a nice flavor of both first gradient methods and first derivative and second derivative approaches. And what's quite good about the way that PyTorch goes about its construction of computational graphs and autodiff means that you can switch between these approaches, which sounds kind of odd, but that for complex optimization problems that can be useful, because if you're working on time critical science cases and you need to fit models quickly, it can be beneficial to start with just simple, inexpensive first order methods that get you at least in the ballpark of where the minimum is, and then just switch to some more sophisticated second order methods once you're there, and hopefully then you can converge quite quickly. So if we put those three ingredients together, we've effectively created some fast numerical iterative solver, which happens to be exactly the sort of tool that might be useful for addressing image modeling problems of this form. So we can compute the forward model in an optimization scheme very quickly, because we can do fast convolutions on the GPU. And then we have exact gradient information and some nice optimization algorithms to help us converge. Moving on to, I mean, this all sounds kind of nice in theory. So I'll now outline an actual application of this. So namely difference image analysis or image subtraction, which I'm sure many people in this community are familiar with. But just to give a brief overview, the basic idea is if we have two images of some astronomical scene taken at different times, we want to fit some model that corrects for the systematic changes in observing conditions between the times these two images were taken. And we can do that by choosing either constructing or selecting some high quality, high signature noise, high resolution reference image or template image, and then fit for this object what we call the convolution kernel, which corrects for systematic differences in the shape of the PSF, and also it encodes differences in atmospheric transparency and exposure times, so your photometric throughput. And then we can also fit for changes in the sky background too. And once we have that model, we can then subtract it from our data, and this gives us an image of residuals or a difference image, which it shows up any variability between the times that these two images have been observed. This gives you a direct way of measuring flux, and also identifying transient astrophysical events. So the thing to note here is that that model, again, is just a 2D convolution with something added onto the end. So it shares this structure that I introduced. And I suppose just a technical detail here, you do, of course, have a choice of how you want to model the kernel. Throughout this talk, I'm assuming it's modeled as a discrete array of pixels. LSST will do something different in their image subtraction pipeline. They adopt a Gaussian basis for how they model the kernel. The discrete array of pixels is effectively just a delta function basis. So it is somewhat more flexible than the Gaussian basis, but it is more computationally expensive to work with because you're fitting in more parameters. So there's just something to be aware of. So we specified the forward model, a parameterized forward model. We want to fit for this kernel and sky background term. So the next step is to write down a noise model, and a convenient way to do that is with the likelihood function. So for conventional astronomical imaging, where we have observations that in like exposure times of tens of seconds, and we're observing with CCDs, we can reasonably adopt a Gaussian noise model. And the negative log likelihood of that looks something like this. So just to walk through the terms here, so this is just the familiar chi-squared, so the square difference between the model and the data over the variances. This is, of course, a function of model parameters. The thing to note, though, is that we also have this additional term here. So we have chi-squared plus these things here, which are uncertainties on the pixels in our image. And these two are a function of model parameters because of photon shot noise. So this is where the non-linearity enters. And this is just a sum over all pixels, 1 to n. And then we have some irrelevant normalization constant we can forget. So in a maximum likelihood framework, we want to minimize this thing. But because of the nonlinearity here, we can't do that analytically. So we need some numerical solver, which again is exactly the sort of thing that we've just built from those points 1, 2, 3 within PyTorch. So we need to compute the forward model at each iteration and update our parameters with respect to this loss function, this negative log likelihood function. Before I show you some results of this, I'd just like to contrast this with the classical approach of solving this problem, because we in our framework, because of GPU, because of running the convolution computations on the GPU, we can do this whole thing very quickly. Of course, if you're attempting this on the CPU, it would be incredibly slow, and this is the problem classical approaches had to contend with. So the idea is, well, can we reformulate this problem and bypass direct convolution computations altogether? So this is kind of similar to how LSST is approaching this problem. And you can, by reformulating it as a standard linear least squares problem. Again, you're assuming a Gaussian noise model here, but you're dropping the dependence of your uncertainties on your model parameters. But this does allow you to then reformulate it as a standard linear least squares problem, where we can specify a design matrix to represent the convolution. So we're not doing direct convolution computations, but we can represent it as this matrix. And then we just need to set up some data vector, and then using the power of linear algebra, we can efficiently solve this system of equations. Of course, the issue here is that you've made a problem that is in reality non-linear, a linear one. So in order to converge to some self-consistent solution, you still do need to iterate. So the way that will work is when you first construct these matrices and vectors, you need to plug in some initial estimate for your uncertainties. Then you can solve the system of linear equations. You get some estimate for your model. You can then update your uncertainty estimates, and then from scratch again, reconstruct the system of linear equations, solve it again, update your uncertainty estimates, and proceed in that way. So this is basically just an iterative process of chi-square minimization. And then hopefully, within 3 or 4 iterations of doing that, you'll converge to some consistent solution. And this works pretty well, but there are, of course, some problems here, namely speed. So although you're bypassing direct convolution computations, you still need to specify the convolution as a matrix, and just constructing that matrix takes a long time. Again, this is more of a problem for the delta function basis representation of the kernel, because there are many parameters, and you need to write basically just a lot of nested loops to build this thing. So this is the bottleneck of this whole process. Also, the scaling with the number of parameters in that kernel is somewhat unattractive, in that it goes with the number of parameters to the power of 2. Again, this is somewhat naive scaling. I mean, there are ways to exploit the symmetry in the construction of the design matrix, but as you'll see later on, I'll use a naive scaling for our method too. And then a third point, quite an important point, is the inflexibility of this classical approach. So you are explicitly assuming a Gaussian distribution for the noise. Gaussian distributions are very tight, so they're very sensitive to outliers. If you're doing a regression under Gaussian noise models in the presence of outliers, the fits can be badly affected by those few points. So in order to make sure our answer isn't sensitive to them, a sigma clipping procedure must be folded into that iterative process of reconstructing the matrices, solving the system, and then updating uncertainty estimates. Of course, there are general issues with sigma clipping about throwing away data, but this also, of course, complicates this issue of convergence, because you're throwing data away at each stage. So it does, again, in combination with this slow construction of the design matrix, cause some issues. But really, this first point is the main point I want to highlight, because particularly for this community that deals with time-critical science cases, we require, well, the faster we can subtract images, the faster we can issue alert streams, and the more science we can do, because the faster we can detect transient astrophysical events. So I'll just show you some performance comparison tests here. So in purple here, this is PyTorch DIA. So this is the software implementation of this fast numerical iterative solver that's been implemented using PyTorch. And this is all run on the GPU. And then we have its classical analog here in black. And this is solved on the CPU. And all computations have been done in Google Collaboratory. So the hardware is equally modest, or at least modestly comparable. So hopefully isn't too an unfair test here, because of course we're using different hardware to solve this problem. And just on the x-axis here, this is the single axis length of image. So and these are square images. So an image of length 1000 on one axis has a total of 1 million pixels in it. And these are just the solution times, the time to fit our DIA model. And you can see, for different image sizes and kernel sizes, the PyTorch DIA is at least an order of magnitude faster than the classical approach to solving this problem. And also, so the difference between the dotted and straight lines here, or undotted lines, are an indication of the scaling with kernel size. And the relative difference between these two lines is somewhat smaller than the classical approach. So it suggests that our scaling, as we increase the number of parameters on our model, is also somewhat better. So just to summarize, so some of the advantages of this approach over the classical approach are the speed, the scaling, and as I briefly mentioned, these are naive scalings for both approaches, because in the construction of the design matrix for the classical approach, you can again exploit symmetries in the problem to speed this up a bit. But because of the special NVIDIA libraries that PyTorch uses under the hood, the scaling with kernel size isn't necessarily linear as it would be for a direct convolution. Like, there can be efficient, albeit not necessarily deterministic algorithms for doing these computations faster than this. But a third, and again, I think this is another really key point here, is the flexibility of our approach. So because we're working in an optimization framework, we have the freedom to generalize the loss function we're optimizing. So this allows us to use things other than Gaussian noise models. So I mean, the Gaussian noise model does require an optimization anyway because of that nonlinearity, but we can also drop in wide-tail distributions if we're working with data in the presence of outliers, or indeed robust loss functions that are less sensitive to outlier data points. So wide-tail distribution like the student's T distribution, or some heuristic robust loss function like a Huber loss. Basically, the Huber loss, it treats inline data points as it minimizes the square difference between inline data points and the model, and it minimizes the absolute difference between outlying data points in the model. So it's just less sensitive to bad data. But these, of course, both provide justifiable alternatives to sigma clipping. And lastly, because our approach makes use of automatic differentiation, we have a flexibility here to change up the parameterization of the model and cater it to different science cases. And again, so as all gradients are done automatically, this makes experimentation and development quite streamlined, as you have the luxury to play around with different models without having to worry about manually recomputing gradients each time you want to try fitting that to some given data set. And so that's all for me. I'll just I'll leave you with a couple of links to the code and paper and my contact details. So thanks very much for listening. I'm happy to take questions now.
Okay, thank you, James. This was very interesting. So do we have any questions already from the audience? Yes, there is a question from Yanis. Please go ahead.
Hi, James. Well, thanks for the talk. So I just wanted you to comment a little bit on the kernel size. So what determines the kernel size that you want to use in these reductions? Because obviously if you use larger kernels, then computation time increases significantly. So what determines sort of, how small can you get in terms of the kernel size?
Yeah, that's a good question. So, I mean, from experience, I mean, so there are. This is sort of a heuristic decision that's baked into a lot of pipelines, right? So normally we say, in order for a good subtraction, we want a kernel that is, so many times the full width half maximum of our data image. Of course, the larger the kernel object you can specify, the better the capability of the model to capture the true variation, true difference in the point spirit function. Yeah, it's I mean, what's nice about the scaling with the direct convolution computations is that there isn't this dramatic computational overhead as you start increasing the size of the kernel, right? Because we no longer have that squared difference. So that this can be particularly useful if you're working with high resolution cameras that have very many pixels. So you can actually work with kernels that would just be totally impractical to use with classical approaches, having to construct the design matrix. But yeah, the minimum kernel size, I don't know if there's like any good rule of thumb as to what determines that. I guess it just depends on your science goals and the quality of the photometry and time constraints at the end of the day.
Okay, thank you.
All right, there's a question from Rachel in the chat. Do you want to say it out, Rachel, or should I read it?
I can pose it myself. Hopefully you can hear me. Great. Thank you for this presentation, James. It was fantastic and super interesting. And I'm interested to know, coming from an observer's point of view, I'm only too well aware of just how widely variable image data quality can be. And I'm wondering how well the algorithm copes in practice with things like variable sky background. What happens when it's non-uniform?
Yes, so so I should just say, all these performance test results, the model that we use is just a scalar for the sky background, but you certainly can implement spatially varying sky backgrounds. We do that in PyTorch DIA, so there is an option to fit like a polynomial representation of the sky background. Of course, the optimization problem becomes somewhat trickier, and yeah, it really, particularly because of your choice of initialization, because it's a priori, it's difficult to know what values those polynomial coefficients do take. So some experimentation is required, but hopefully data sets will share some commonality. If you're working with some data set, they should be around the same sort of values. So I'm just talking from experience from working with some data. So you do eventually get a good idea of what those should be approximated as initially, but it does require a bit of heuristic experimentation, as there is an extra human overhead there if you're working with spatially varying backgrounds.
Thank you.
We have another question from Bruno.
Hi, James. Excellent work. Really nice. So I wanted to know if the algorithm that you're using would support, I don't know if it supports already, regularization on the kernel, like any kind of penalty on that.
Yeah, so that's again pretty straightforward to achieve because of the automatic differentiation tools. So it's straightforward to just add whatever penalty you would like to, any reasonable penalty, onto whatever loss function you're optimizing. So in the code PyTorch DIA, we introduce Laplacian regularization onto the kernel pixels, which is basically like just a connectivity graph on the kernel. So it favors pixels to have similar values to their neighbors, so you get smooth kernels. But it's straightforward to just implement straightforward L2 or L1 norms on the kernel pixels also.
Thank you.
Okay, are there any questions left? Yeah, there is a question from you.
Hi. My question is, does this approach produce less artifacts than the traditional method?
Yes. One major source of artifacts, again, I just talking from personal experience, is that your convolution kernel isn't large enough. And again, what's nice about this approach is that it scales much better with larger kernels, so you can sort of get away with experimenting with larger models. But ultimately, the image model, the model itself that we're implementing, they are directly, they are identical to the classical approaches. I suppose the key difference here between the models I'm implementing in this work and LSST are the choice of basis functions for the kernel. So I mentioned that this is a discrete pixel array, a model for the kernel, which is more flexible than the Gaussian basis functions used in LSST. That's useful if you're working with a somewhat irregularly shaped PSFs. So I'm not sure if that's the case for LSST. Other than that, it's just the size of the object to represent the kernel. Because that scaling is better, that can go quite a long way to helping beat down some artifacts.
Thanks.
There was another question from Yanis in chat. Do you want to say it out loud?
Yeah, sure. Have you run any comparisons of the photometric quality of the crowded field stellar light years that you get from your method with those obtained from standard PSF fitting algorithms, such as IRAF or Deophot? Or do you not intend to do so? Because DIAs generally outperforms PSF fitting in very crowded fields. Or do you plan to do something like that?
I haven't done the direct comparison against PSF fitting photometry, but in the paper, we do a direct comparison between its classical analog. We don't do the comparison at the level of the light curve, but we do use proxy metrics for that give an indication of quality, and we do show equivalent photometric performance at the level of precision that you would typically reach with conventional imaging. We're somewhat less precise, but at a level that doesn't really matter, because as we're running computations on the GPU, in order for these to be fast, we need to work at single floating point precision rather than double. But ultimately, in terms of if that were to be an issue, your photometry would have to be exceedingly good. And in practice, it shouldn't be a problem.
Thank you.
Okay. Any other questions? So I don't see anything else. And with that, I would like
There is a raised hand, I think.
Oh, yeah, but Lou, do you have another question, or is your hand still raised from the previous question?
Nope.
Sorry, okay. All right, so with that, I would like to thank James again for this interesting talk, and thank you everyone who also joined the colloquium today, and I will see you in a month. Bye.
Thanks very much.